This next session will be the perspective from the funders. We keep kind of expanding this session's length every year because y'all have a lot of questions. And so this year, they get Kelly from NSF is going to be talking for 20 minutes. We can ask her questions during that 20 minutes if she gives us time. Thorsten's going to come talk for 20 minutes about NASA, and then we have a 20-minute discussion dedicated to kind of talking about the funding agencies, funding for our science, and what the future holds. So with that, I'm going to hand it over to Dr. Kelly Brunt, if I can find your slides.
They're there, I promise.
Right here.
Awesome. Not even going to risk it. Yeah, I'm Kelly Brunt. For those of you that don't know me, I am now the permanent program officer for Antarctic glaciology, and that's a change. So that's been about 2 months old. More about me. I'm probably one of the few people not looking for gators around here. I intentionally am on the 6th floor. I want nothing to do with them. So you guys have at it. Definitely don't want to see any snakes. I'm not going to lie about that. All right, so I thought I'd just go through. We've had some changes at NSF, not too many actually, but like I said, I'm now the permanent person there. I've chucked my email up there. You can usually, if you just Google NSF OPP org chart, you can usually find all the relevant people for the relevant programs. Obviously, a lot of you guys know Dave Porter. He's an IPA, handling the oceans and atmosphere side of the house. That's another one that intersects this community quite a bit. And Mike Jackson, who's currently in Antarctica. He's the third person that I say is probably one of the more relevant folks on this list of names for folks in this community. And I'll just point out Marion Derek, horrible with that. Asterix, Obelix, those Belgian names. I'm so sorry. I know I butchered that. But she's brand new. She started kind of as Vladimir's IPA, but more importantly, she's also heading up our polar cyber infrastructure program. So that's also probably pretty relevant for this community. But again, Google NSF OPP org chart, and you'll see all this along with the Arctic side of things. These are the programs. The Antarctic side of the house is kind of busted up pretty much by discipline, which is kind of easier to navigate, I think, in some respects. But here are the various programs we have on our side. Matt was talking a little bit earlier about things on the horizon. He talked about IPY in 2032, 2033, and he also talked about the NASA decadal survey, and I'm sure Thorsten will have comments about that. But I also want to point out that the OPP Antarctic Sciences has a document that we use to kind of help us navigate waters. What is the community told us our priorities, research priorities in our world. And that document's called Future Directions of Southern Ocean and Antarctic Nearshore and Coastal Research. It's long-winded. And that document kind of outlined four priorities. Some of them very, very theme-specific, how much, how fast. That's probably the one that most affects the people in this room. Another one has to do with biota, and a third one has to do with the universe and whatnot. But that first one is probably very key for us. But also, just as key as those three sort of thematic elements is this bullet at the very top. We also have to maintain this core program of good science in Antarctica. The best science, and of course, the science that has to be done in Antarctica, because it can't be done anywhere else. So one of the reasons I am really pointing to this is another area. You see, it's sort of a decadal plan, but written in 2015. So you can imagine in coming years, we'll be looking to refresh that. And I would strongly encourage you folks, if you had an interest in what that says going forward, especially if you're mid-career type folks, senior career type folks, reach out to NSF, and we can see if we can make a marriage between you guys and the national academies, who will undoubtedly be the ones spearheading something like that again. Try to stay informed, and there are ways to stay informed. There's a couple of resources I really don't want to read right off the slide, but try to stay informed. I think I know we've been putting out some difficult Dear Colleague letters, and I'll get to that in a minute, but I will say that I think one of the things that I've seen in recent years is how much those Dear Colleague letters are coming out from the NSF and kind of giving that message, trying to tell the community in as close to real time as possible, like what's going on, what are some of our limitations and challenges, what are our opportunities. But try to stay informed, and here's many of the resources. The one that I sort of like the most is CryoList, and that's because we make sure that almost everything that's going to have an impact on you folks, or opportunities presented to you folks, I certainly make sure that goes out to CryoList. So if you're not on that, please. And I saw a lot of hands go up for first-time WAIS workshop attendance, but I just want you guys make sure, please, you're all on CryoList. Just a little path, I think, at NSF. The first thing I want to say is, again, there's a lot of early career representation at this workshop. I want to encourage all of you to make sure that you have good mentorship in place. And that's on you. That is your personal responsibility to make sure that you think you're getting the mentorship you need, either through official structure in your departments, or by you just kind of going out personally and making sure that whatever need you have as far as mentorship goes, that you're reaching out to the right people, maybe inside your institution, maybe at this meeting. Look for those folks. The joke that I always like to make is nobody gets up in the morning and says to themselves, I'm going to go mentor the heck out of Kelly Brunt. You have to take personal responsibility, your mentorship. I don't want to get a call from somebody when it's too late. So please make sure you have that kind of set up. But here's sort of a little flow chart on the right of kind of the types of opportunities we have at NSF for various career states. Obviously, starting with the Graduate Research Fellowship. Anybody been a recipient of one of those in this room? Good to see. The Doctoral Dissertation Improvement Grants. These are kind of smaller. They're just intended to kind of get you over a bump. Right now, we have them on the Arctic side exclusively. I'm pretty convinced this is a creative room, and you could figure out a way to script that up if need be. But watch this space. They're not part of the Antarctic program yet, but watch that space. Postdoctoral Fellowship. Who's been a recipient of that in the room? Great, awesome. And then we have, the regular awards fit in between, just our regular solicitation, regular awards. But then we have these career awards, kind of intended to help you blend your research and some of those, early teaching type responsibilities and educational responsibilities. Who's been a recipient of a career award? Awesome. And then finally, one thing that I don't think we push enough are the Mid-Career Advancement Awards. Anybody been a recipient of one of those? Yeah, I knew it. So keep an eye out for these, please, because I think this is a really important part of your career. I think we have done a lot to help early career folks, you can see from that list. And we've put in an artificial step between early career and mid-career. We made it hard. One day, you can no longer tick that box that says early career, and suddenly things get wicked challenging. I think let's focus a little bit on making it a ramp. So keep an eye out on the mid-career. Send me an email if you're interested in something like that. But I think it's an area of focus that we need to really, really look at. This is just a little bit of advice. Again, I've talked about us being in sort of challenging times. We currently don't have an Antarctic fieldwork solicitation. I put 2 links at the bottom of this that kind of point towards recent Dear Colleague letters, DCLs, that address this. That, we had a hiatus in 2024 of our field solicitation. So keep those 2 words in mind, right? Hiatus 2024. We don't have a solicitation yet, but that hopefully gives you a timeline of what the challenges are on that side. The other link here, and I can't remember which is which, I apologize, but the other link here is to sort of a different type of Dear Colleague letter that sort of drew out where some of our, what I call pinch points are, and the time scales associated with those pinch points. So make yourself familiar, even if it seems like it's a little bit out of date. These DCLs, these Dear Colleague letters that address this, do give you a good sense of what the problems are and what the time scales are for those challenges. But with all that in mind, here's just a little bit of advice. We want you to kind of manage your research portfolios like you would manage your finances, and think about diversified portfolios or diversified proposals that you're putting in. Think about field and non-field, think about different funding agencies, working with maybe international collaborators. We'll get back to that in a second. But be really diversified about it. Non-field work proposals are really attractive to us right now, obviously. We heard a lot of great talks this morning, Roger gave a great talk. I think Caitlin gave a great talk. Veronica gave a great talk. All of these were based on data that was already in hand. And that's important. We also have a person from the USAP DC sitting in the back of the room. We got somebody representing the Polar Rock Repository. I encourage you to go to that meeting on Thursday and talk to these folks, because a question came up. How do we, what type of data sets are out there? What would we want to be looking at? Go to that meeting. And then, when you write a proposal around it, smack us upside the head and remind us inside the proposal that we've said this is important. Sound good? So we are interested in these data sample and reuse proposals that come in. We've spent definitely tens, probably hundreds, maybe not too much more than hundreds of millions of dollars to collect these data sets, bring them home successfully, and then archive them. So let's really hit them for all they're worth. The other thing I'm going to add in here is being realistic about timelines, delays, and goals. And what that kind of speaks to is, for early career folks especially, if you're thinking about tenure, I'm not convinced that a field-based proposal right now is the way that you should be sort of putting all your eggs in that type of basket to get to tenure. And the reason is, look, we've got a hiatus. There's long timelines of writing those proposals, getting them accepted, then fielding them, and now think about the tenure track timeline. These timelines don't line up. So be thinking about that on, if your tenure track, certainly have one of these out there, but also have these non-field type proposals kind of underneath you as well. Again, that points back to diversifying your portfolio. Working up in size and scope and whatnot, that kind of talked to the slide prior to this with the flow chart and whatnot. 2-pagers. If you have a research idea, write it up as a 2-pager. If you all think of the front page of a proposal with the sort of overview, the intellectual merit, and the broader impacts, that's not what we're looking for. We're looking for a 2-page document that gives us a sense of what you want to do, how you want to do it, what are the challenges, describe the gap in knowledge that you're trying to address, give us a rough sense of budget, give us a rough sense of what you want to do for broader impacts, write that up fairly informally, send it to the program officer you think it intersects most with. We'll take a look at that. We can maybe shop them around behind the scenes, find the right place for that, and we can get back to you. But I strongly encourage you to send us a 2-pager with your ideas so that we can help you kind of navigate some of NSF's complexities. And again, the Dear Colleague letters, good links for those. I just mentioned intellectual merit and broader impacts. Those are the 2 main components for NSF proposals. I was going to take this slide out. I decided not to. I just want to speak really quickly to broader impacts. It's always been a challenge for the community to really get their head around these. I'm just going to say a couple things about broader impacts. They're just that. They're broad. There are no real bad ideas when it comes to broader impacts. I think the challenge for this community is to write a compelling story about what you want to do. Sometimes it's as simple, seemingly as simple as training the next generation, but you could write a compelling story around that, and that'd be just fine. What we are seeing reviewing quite well is broader impacts that are a little bit focused. In other words, don't do the shotgun approach. We're going to do everything, and we're going to dedicate a half a page in our proposal describing that. Be a little focused and tell a compelling story around it. And that's all I really wanted to say about that slide. If you have any other questions on that, though, reach out to me. And this is my last slide. Don't worry, I'll have Thorsten come up, and we'll leave more time for questions in a sort of group setting. But the last thing we want to say is, get involved. You can sign up to be ad hoc reviewer or a panelist. A lot of you have probably seen the surveys that we've started sending out, which I think are great. Being a panelist. And so raise your hand if you haven't. This is making me more nervous. Okay, we're trying to get those around to folks to, get people to, we were all working with old Excel spreadsheets, potential reviewers that just got handed down and never refreshed. And so now we're trying to figure out a little bit more systematic ways of reaching out to the community and saying to you, would you like to volunteer to be an ad hoc reviewer? Would you like to volunteer to be on a panel? And I just want to say one really great thing about panel service, and that's the last phrase, I think. You really get to see the sausage-making process. It really gives you a good sense of, what the panel and, a subset of the community feels is A, an important idea, and B, a well-written proposal. So it's a really good thing to do, especially as an early career, but then refresh it periodically, because I think panels evolve through time. One of the things that I think I'm seeing as far as evolution is, let's go back to broader impacts. Another thing that's reviewing really well about broader impacts is a way of assessing how they're doing. It doesn't necessarily have to be perfectly quantitative, it can be qualitative, but looking for strategic ways of assessing things is now reviewing really well in panels. So things evolve through time. So get on as an early career person, get yourself, up to speed on what folks see as really good proposals, and then keep volunteering over time. Not every year. I don't mean that. I'm not trying to set you up for long-term service, but occasionally check back in. I'll let you guys read some of this, but the last thing I want to say is consider joining us. We have, not just panel service on that sort of, couple weeks a year, but also think about, we have permanent positions that we, announce periodically, but we also have rotator positions, or what we call IPAs, Intergovernmental Personnel Act type positions. They're 2, 3, with an act of Congress, maybe 4 years of joining NSF kind of on a temporary basis, somebody coming in from the community and kind of giving us a sense of, what the community is really thinking right now. On that list that I showed you before, people like Becky Gass, Dave Porter, Marion Derrick, those 3 folks are IPAs currently with us. And then, talk to the program officers about opportunities. And I really think that was my last slide, and with that, I'll turn it over to Thorsten, and we'll take questions at the end, or, all right.
Hi, everyone. Thanks for coming to WAIS. I really like WAIS. I try to come to every year, and most of the time I make it, even if it's a short time. For a short time. Thanks again. For those of you who don't know me, my name is up here. I'm Thorsten. I'm managing the Cryospheric Sciences program at NASA headquarters, so everything ice. In addition, I manage National Snow and Ice Data Center, the ISA-2 mission, Crystal missions, and some other missions that are in competition right now. So that's kind of like overall what I'm doing. So, and I'm pretty much a point of contact with anything related to cryo. Since this is a group with lots of NSF people, lots of early career scientists, I thought, let me start with something different. And Matt mentioned it, and Kelly mentioned it, the decadal survey. Every science discipline or organization at NASA has a decadal survey, planetary sciences, astrophysics. They all have a decadal survey that comes out every 10 years. We ask the National Academies of Science, Engineering, and Medicine to come to put together a committee and develop a decadal survey. It's a pretty big book. It's like, over 100 pages, etc. And this one came out in 2017. It's called Thriving on Our Changing Planet, a Decadal Strategy for Earth Observations from Space. And this is more than just a guideline, as I said here. It tells us what missions NASA should implement, where should we focus our money on. And then it also tells us things we should do end-to-end modeling. We should do modeling not only for exploration, but also for how does it benefit society, and how do we inform stakeholders, users, etc. And also recommend open science and things like this. So this is a big book for us that really determines what we should be doing. Now, independently of this, we have our science program. For example, Cryospheric Sciences is to some extent independent of what the decadal survey says, but obviously not totally. So in the last decadal survey, and I'm being really quick here, the decadal survey had 5 designated observables. They're lined out here. And the first 2, clouds precipitation and convection and aerosols, were put together in one mission called Atmosphere Observing System. Then we have mass change, which is basically a GRACE follow-on. We have surface deformation and change, which is an interferometric SAW, which is pretty much a follow-on for NISA that hasn't even launched yet. And then we'll talk about NISA in a second. And then a hyperspectral imager to monitor surface biology and geology. So those missions are all in implementation right now. After all, they were selected, 8 years from now. So in addition to this, to these missions that are being implemented, the decadal survey recommended decadal survey incubation mission that will maybe launch in 10 years from now but they need to be developed. Requirements need to be developed, measurement needs need to be developed, etc. And we have, the decadal survey has 2 of those, planetary boundary layer and surface topography and vegetation, which includes the ice sheets, and Matt and some others maybe in the room are on the science team for STV, for surface topography and vegetation. Again, this is something where the science community tells us what we should be measuring, what quantities, with what resolution, spatial, temporal, etc. And then we have the Earth System Explorers that are missions that are being selected for development, $300 million missions to be launched in 2029 and 2031. We just selected 4 missions to do a phase A study, concept studies, and we do a down select to 2 in about a year from now. And so we selected those missions that measure greenhouse gases, ice elevation, ocean surface, winds and currents, ozone and trace gases, and terrestrial ecosystem structure. So those are the things that are going on in parallel right now. And the important part is, and I think I have it on one slide, is, although some of these missions, they don't have cryopolar as a main objective, most of our satellites go over the poles. So I encourage every person, try to get involved in these missions, in these development science team. Like, for example, planetary boundary layer. When I was a CI scientist, that's where I'm from, planetary boundary layer, atmospheric boundary layer actually is super, super important for heat exchange, for all these things. When I did polynias on my PhD, super important. If people develop a mission to measure atmospheric boundary layer, it's very important that we have a polar person represented on these teams so that the polar planetary boundary layer is included in the discussions in the development of science requirements. Earth science to action. Let me skip this. This is kind of boring. No, I shouldn't say this. All right. My boss, Karen Saint-Germain, the director of Earth Sciences, her big vision is Earth science to action. So the 2 objectives are holistically observe, monitor, and understand the Earth system, and to deliver trusted information to drive Earth resilience activities. And what it basically means, and here's a strategy in a bigger picture, it's like this pyramid. We the scientists, we at the bottom there, we do this foundational science exploration, this, technology to development, etc. But it trickles up to the user, to the stakeholder, to the people who need our data. So there has been, there has been quite a bit of focus because of that on wildfires, on agriculture, and it's tricky times right now for polar. Where does polar come in? And we are pitching it, for sea ice. We have increased with the shrinking sea ice. We have increased marine transportation, ship security, navigation. Those things are becoming a topic. For ice sheets, we have basically sea level rise, and where it gets tricky, if we talk, Earth science to action, we think about, like say a 5-year horizon, time horizon. And then the perception is sea level rise is an oceans problem. And I'm trying to make the case almost every day. I'm not lying. That sea level rise is an ice sheet problem. As I'm preaching to the choir here, so it's easy for me to make this argument. How the biggest uncertainties in future sea level rise is, by far the biggest uncertainties in the ice sheets. The biggest contributor is and will be even more so the ice sheets and glaciers in any case. So, but that's, further out. We're talking about, 2100, and you hear, these comments from politicians. What do I care what's happening in 2100? Climate change is a hoax, etc. It flares up again, which is kind of interesting. I thought this topic was done, that climate change is a hoax, and then it flares suddenly up again. People start believing it again. So Earth science to action, Earth action has become a big topic, and that's where we're struggling a little bit with, not only cryosphere, ozone, et cetera, ozone science, to where do we see our applications? And if you have any thoughts on this, I'd gladly talk with you more about it. But right now, the angles we have is sea level rise and pretty much, marine transportation and U.S. national security. So some general updates. I'm talking too much otherwise. So the Earth Science to Action strategy is out. It's a little booklet you can download. If you type NASA Earth Science to Action strategy, you immediately find it. We require now for larger proposals an inclusion plan. We want to be a more inclusive, a more diverse community. So we ask our proposals to have an inclusion plan. And especially for bigger proposals, this is where we can make an impact. If PIs of bigger efforts start thinking about how do we train a diverse workforce, how are we improving on inclusivity, and I think there are lots of things we can do better than we have been doing. Open science, open source science is now a requirement in proposals. We are moving very strongly towards it. It's a little bit of a what is it? What's the word? It's a big change of philosophy because for many people, for many PIs, my science is my livelihood. And we are all competitors, and like every 4 years I write the same proposal because I'm the expert here, and I'm holding my source code very close to my chest. Nobody else can do it because nobody else is as good at it. So 3 years from now I'm getting funded again. And being more open, it can be challenging. It's a little bit there's certainly some friction there in our community. I realize that the early career scientists and young scientists, they grow up with, sharing code and sharing data in a GitHub environment, et cetera. But it's a little bit of a philosophy change. Similarly, starting with ROSES 2025, the dual anonymous peer review process will be the default process to review proposals. So what this means is that PIs write proposals. I should actually talk about ROSES for a second. ROSES is our annual announcement. It comes out on February 14th, and it's called ROSES, and it stands for Research Opportunities in Space and Earth Sciences. So all proposal opportunities, not only for cryosphere or earth science, but all of them are being published on February 14th for the entire upcoming year. And it's an important date. When this comes out, people go to NSPICE, to the NASA website, and look through all the research opportunities that are out there, including the cryosphere call, obviously. So starting in 2021, the dual anonymous peer review process was started. For earth sciences, astrophysics has been doing it for much longer than we have. And what this means is PIs write proposals where they hide, if you will, their identity. They write proposals in an anonymous way. And the idea is to reduce unconscious biases in proposal evaluations. And there was a lot of pushback initially from the community. I started it early because as soon as we learned it will become the default process, well, I can fight it for a little bit, but let my community have a head start. So and it seems to be working. Panelists, some of you may have been on a panel recently. I know some of you have been on a panel recently. Thought this process is really working well. We have our panels, we talk proposals, we don't talk people anymore. We just evaluate the proposals. The science the proposal discussions are all really about the proposal. And people feel liberated in many ways that the PI's name, the PI's face, the PI's reputation is not part of the discussions anymore because we all develop opinions about people. So that seems to be working really well. You know, maybe as a consequence of the NSF report about field safety, we are doing field safety, we are more trying to be better in terms of field safety at the headquarters level as well, especially with our, you know, long airborne campaigns. PACE, an ocean biology mission, launched in 2024, which is really great. Take a look at the data. If you're doing ocean biology, etc., in the polar regions, fantastic data. NISA, which will provide, it's unprecedented data on not only of backscatter, but also of interferometry, will launch now no earlier than February 2025. And we are operating under continuing resolution until December 20 right now, which means we have money until December 20, and then we don't know what's going to happen. It's a tricky situation for you who are PIs under, you know, for NASA. You know how it works. You know, I send money in small chunks because I don't have any more money than I have until December 20th. And, you know, and with the new president, et cetera, we don't know when this continuing resolution will end. They probably put an extension in for another month. And then what happened 2 years ago, we finally get a budget in March when half the year is over. And then they tell me, hey, you get, you know, $500,000 less, deal with it. And I have made my commitment. It's a tricky situation. So I'm trying to be, you know, sending out money as much as I can, and I think you all get money, otherwise complain. But I think we do have money to work, so it's all good. Very quickly, so I'm managing the cryospheric sciences program, but there are lots of other opportunities out there in these ROSAS calls for cryospheric sciences. This is something I want to remind people. We have the modeling, analysis, and prediction program MAP that comes out that has pretty big budget to do modeling studies. We have physical and biological oceanography. We have sea level change team. We have interdisciplinary sciences. That comes out, I think, every 4 years. So not every year. Earth surface and interior, if you're doing, you know, bedrock and things like this. You know, that may be a good opportunity if you want to create a big data record, making Earth system data records for use in research environments measures may be a good opportunity for you there. It has a lot of money. I think the annual amount is like $600,000, $700,000 or so. So it's worthwhile applying. And then there's specific satellite teams. As I said, even though the primary objective may not be cryo, most of these satellites go over the poles, and it would be great to have, you know, scientific cryospheric representations in those missions as well. Furthermore, we have some early career and student programs. Those are some slides I've shown before. The new investigator program is now called the EKIP, or Early Career Investigator Program. It's a small program, but you can basically propose whatever you want, which is kind of great. And then we have Finest, which is an annual solicitation for graduate students. The professor is the PI technically. It's not a fellowship. It's very important because sometimes people get this confused. To be honest, it's a great program. It's oversubscribed, and it makes selection rates really low, and I'm very frustrated about it, and Matt is frustrated about it. I see you smiling. It's hard, right? It's a great program, but it's the selection rates. I forgot what they were. They were 5-6% or something like this. It's awfully small, but it's a good practice to write a proposal for a student. Interagency. Let me skip this slide. It's too much stuff on it. I'm running out of time. Let me talk a little bit about the road ahead. So we're developing new satellite missions. And, you know, even though, as I said before, cryosphere, polar science may not be a prime objective, most missions are in a high inclination orbit. That means they go over the poles. You know, most satellites are like a sun-synchronous orbit. That means they take measurements up to, you know, at least 82 degrees, 83 degrees, depending on swath widths, even higher. So lots of data over the poles in pretty much all these satellite missions. We're developing new airborne capabilities. We asked the national academies for a study whether NASA needs to have a big airplane. That report says, yes, we need to have a big airplane. And it's mostly because of the atmospheric scientists. They like to have like 20 instruments on their planes at the wingtips and the bomb bays and everywhere. Sensors. For Icebridge, we have, Caitlin and Kirsty know this well. We have like, 4 or 5 instruments on it. But NASA purchased a 777 in any case. It's a monstrous plane, it's big, has a long range, it can fly for 15 hours or something like this. And it can easily reach Antarctica or any point in Antarctica, which is a new capability, which is kind of interesting. Flying out of Ushuaia or Punta Arenas can be tricky because it's such a big plane, but it provides a new opportunity, and it should come, be ready in a couple of years from now. It was a commercial plane that right now taking all the seats out, cutting holes in the bottom of the plane, etc. And we are still investing into unmanned airborne systems, and that's something that's, I think, becoming bigger and bigger. I was just at a meeting 2 weeks ago in Tromsø, and we talked about it. We talked with the Norwegians about it, flying out of Troll, etc. And when it comes to rings or so efforts like this, UAS, especially in Antarctica, can play a big role. And we had a request from Congress 2 years ago in the appropriation where we were asked, hey, can you, NASA, look into the feasibility of using UAS for operational monitoring of the Arctic? So it's I think there's a lot of potential there. Planning for the next decadal survey. I talked about the importance of the decadal survey to NASA, what NASA is doing. The next decadal survey is coming out in 3 years from now. And I think next year or so, the National Academies will put together their committee that will write the decadal survey. And what I want to do, and some people in the room know about it, we'll put together a small working group to come up with a white paper that tells the Decadal Survey Committee what NASA should be doing. In the last Decadal Survey, the one observable was basically ice elevation. And the question I have, maybe, for you and to discuss, unfortunately I have to leave before the end of the meeting, is ice elevation, if you could measure if you want any measurement over Antarctica, in this case, would it be ice elevation, what you wanted, what you needed, or would it be something different? I have opinions, but it's something that I want to discuss with the community. What do we really need? What do we want the Decadal Survey that will write in a very important document what we should be measuring for the polar region? What should this be? The technology is a different story. The technology will be developed, the requirements will be developed, but what does the community need in terms of observations, satellite observations, so big picture observations that we should, NASA should try to make. International Polar Year is around the corner as well, so it's getting interesting. There's lots of things that are going on. I understand the Polar Research Board at the National Academy, and so they just put together a planning, IPY planning committee, the National Academies. And so if you're on the committee or know anyone on the committee, please talk to these people. I think they will have a meeting my understanding is in February or so. That committee was just put together, I think, like a month ago. I don't think they have ever met. I encourage my community, as some of you know, to apply, to be on this committee, or to recommend people. So this is very important because it defines the US's role in IPY. And if US science is well represented in the IPY planning, it will trickle down for sure to Kelly and me, hopefully. That, it will affect, probably, hopefully, our budgets, because it's a big thing. So it's very important that, NSF science, NASA science is well represented in the IPY planning committee because it has real impact. The other thing is, WAIS, as you guys know, is jointly funded by NASA and NSF. So, and while we have, to some extent different priorities, I like this workshop a lot, and also because, this workshop can act as a catalyst for, to establish interagency collaboration. And we've been working with Paul Cutler, now with Kelly, we're working a lot about, how can NSF, NASA collaborate better? We have some joint proposals like this one, but we're thinking about having a joint call out, and it's something that's still in the planning processes. So this is something for the discussions during the meeting here to have in mind. Hey, this is a joint NASA ESA meeting, NASA NSF meeting, and what can we actually? Where can we join forces to be even more impactful as compared to a single agency effort? And I think that's I'm pretty sure it's my last slide. Yeah, it's my last slide. Thanks so much.
Come on back up, Kelly. You guys can sit down over there. You don't need a stand. So we have, 15 minutes, 20 minutes for some open discussion with our funding agencies. Is there anyone interested? It looks like Marion can't wait to pop up and ask them a question, so you can kick it off.
Thank you. Thank you for both of your presentations. I know a few months ago there was a conference held to have NASA and maybe NSF was there, but to chat about the future of ocean drilling and IODP. And I'm just curious what came out of that and if a joint effort from NASA and NSF for future ocean drilling projects is potentially on the docket. Thanks.
Is the green light on?
Problem solved. So, good question. I don't know. I have no idea. I know that workshop happened. I haven't heard any report out or anything. Good question.
And it's on the ocean, I think you just mentioned specifically the ocean sciences, and OPP is kind of one of the only geographically defined areas, and it's just outside. I don't know. I apologize, but we can shoot us an email, and we can help you find what came out of that. Sorry.
Kelly, since you have the microphone right now, we've talked at this meeting over the past 2 years about the new Antarctic research vessel, and it's been a little quiet on that front lately. So is there an update for this community?
I don't think there is, and I apologize. Dave Porter sent me some information this morning about, he's really the guy to talk to on the science side of things. And then, of course, my colleagues on the Antarctic infrastructure and logistics side of the house. The Antarctic program at NSF is divided into two sides, the science side and the logistics side. Dave sent me, an announcement was sent out looking for, a team to have finalize the design. Other than that, I don't know too much about that, and I apologize. That's 2 blanks on us, sorry. But Dave Porter's the one to reach out to. But my knowledge, and I apologize for that.
Yeah, thank you both for your talks. You can probably predict this question, and it's probably going to be a blank too, but I'm wondering if you have any idea when proposals involving fieldwork could be accepted again.
3 for 3. Okay, so apologies again. We can only talk about solicitations that are actually active. I mentioned if you always go back to those Dear Colleague letters. Even though they seem like, oh my gosh, they're dated, they still provide glimpses of timelines. And in the most recent, hey, you know, we're putting a hiatus, was the word, on field proposals for 2024. That's the best I can give you. I know that's not an answer, but watch this space. Make sure you're on CryoList. Watch this space. I know it's been a challenge. My hope is that, you know, we took this hiatus. Hopefully we get ahead of things a little bit. You guys know what the pinch points are. It's basically beds in McMurdo, beds at South Pole, fixed wing flight hours. I'm hoping that on the other side of this, we'll be better poised to continue to do, you know, to fund and physically support what's next and the great, you know, science to come. I think it's important for the NSF and for you folks, like, how do we do things better? You know, we got to stop bringing lumber into the field. That's you know, things like this. I think when we're looking at budgetary concerns too, we talked about this a little bit last night. We're looking, you know, to have you guys help us find not just budget slashing measures, but what are the next cost savings measures? Those are two different things. How do we get more creative? Is it UAS, UAV? You know, what is it that takes us into the next generation where we can be a little bit more resilient to these challenges? But we're looking to get input from you. We're looking to sort of think outside the box. But I hope that this hiatus will allow us to be better poised to go into the future with those thoughts in mind. Oh, sorry.
Yeah, just a quick comment. You know, be creative, because we needed to get some, you know, GPS stations out to Antarctica for NISA validation, specific locations. And, well, we couldn't send people out, so we had a meeting with Mike Jackson. And it's now the technicians who are doing it. They're deploying the GPS stations for us. So it's not a satisfying answer, but, you know, maybe, you know, technicians can do some of the work at least too. Or we had the same was done with NSF in Greenland, where we had technicians dig out some measuring devices or something like this, or replace batteries if that's what's needed.
I got one more comment. I just want to make one last comment on this before we move on, and that is that keep in mind this hiatus was associated with new proposals. Currently, we are still doing, right now, we're doing science in Antarctica. There are teams down there, and that's an important thing to remember. This wasn't a total hiatus on science. This was a hiatus on new proposals coming in to help us catch up.
See, I want to follow up on two comments y'all made. One on Thorsten's side. In your description of sort of the arc of development, you're saying, okay, what are new observations we need? And then right at the end, you said orbital, right? What do we need from orbit, right? And so some of our core observations, like ice penetrating radar, are mostly from airplanes. I know there's discussion about whether they could happen from orbit. I have my own feelings about that. But there are technologies that we mature and rely on that don't go to orbit. So that's statement one. And I think in the NASA context, how we develop and mature technologies that are not pointing towards orbit is a thing to think about proposing. To go to Kelly's comment about sort of, you gave us some good creative ways to think about proposals that were post-data, how you could do science, and you gave examples of talks earlier of what you could do. But when we're developing technologies and can't go to the field, it'd be great if you could articulate a version of how one would do that without the field. So like if we proposed, in our group, we often bounce radars off of a gym. If I was to write a proposal to you where all we ever did was measure a gym on campus, would that be a compelling Antarctic glaciology proposal?
You're a really good writer, and I would imagine you could make it compelling. But I would argue that, you know, one of the things that was said to me when I first came on with NSF and OPP was that the Antarctic program has to think a little bit outside of 60 degrees south. And so there are places you can go to look at ice that are outside of 60, and maybe we could co-fund. Thorsten did a really good job of pointing out other areas outside of cryosphere that actually intersect with cryospheric sciences, and I didn't do that great of a job of doing that. But one of them is in earth sciences, like the geomorphology and land dynamics group. There's other places around NSF that we can, behind the scenes, go and look for co-funding or help, and that includes people inside OPP. We could go to the Arctic section. So this goes back to my two-pager comment. If you have an idea, send me a two-pager, and we can figure it out. We can work through that. One of the things I like to say is this is not your advisor's OPP. Ultimately, we are doing a really good job behind the scenes of looking for co-funding opportunities inside OPP and outside of OPP. It's been a really, really good thing for the program. And I'm just going to make a comment for Thorsten, sorry. Just because the technology doesn't exist yet, don't hesitate to bring it forward to Thorsten, because it's 10 years.
Yeah, so with regard to technology, Dusty, we have these different technology programs. AIST, AI, Advanced Information System Technology, and Advanced Instrument Technology, something. Sorry, I should know all the acronyms.
Lots of A's and T's, yeah.
So that's something, to really look into. IIP Instrument Incubator, that needed to have its path to space defined, which was always like a tricky part. But we are recognizing more and more, we need to be able to sustain also airborne instruments and develop, airborne instruments. So,
So in that, if someone was to propose to an AIST call and say in the path to orbit, we have no intention of it ever being in orbit, it will go to airborne surveys within NASA, do you think that could win?
So if you have an idea, let me know. I could talk to the program manager about it. I think that requirement is softening because people realize, some instruments just, need to stay airborne. LiDAR tech, blue lasers, etc. They will never be shouldn't say never, but yeah, same thing. Or radars. Radars like to fly low, and as we move forward with UAS, etc., we bought this 777, as I said. I think airborne instruments are more than just find us to space. Yeah. But let's start.
Thank you.
Mm-hmm.
Brent?
In the spirit of interagency collaboration, apart from this workshop, what are NASA and NSF co-funding in Antarctic cryospheric research at the moment?
Click.
Mike.
Yeah.
Thank you.
And then, I don't know how much you want to talk about things like LDB. ISAT 2 has had support in the Antarctic program. A lot, NISAR was brought up. Sometimes it's not just sharing a budget, but NSF is the facilitator for getting all good science into Antarctica. And so there's definitely collaboration between the support side and the NASA science side. So there's quite a bit. The ground calibration for satellites, LDB, and a couple kind of working groups or conference.
Got it. But as far as the near future, your programs, you don't really see that happening.
No, I think we're working towards doing this. We are planning to do this, like come up with a joint call. The other thing what happened in the past, I don't know whether we do anything for Antarctica, but certainly for Greenland is if there is a big NSF call out with a strong NASA component, and what happens is the NSF scientists submit their proposal. At the same time, the NASA scientists send the same proposal to me with a NASA budget. And so NSF will do its review process. I won't touch this proposal until that is completed. If NSF says we are funding it, it's a great proposal, we are funding this proposal, I will then fund the NASA portion and the NASA scientists to be part of this effort. And that happened several times. It happened, the last time was, what's it called, Green Arc, whatever it's called? I forget. So where I fund the NASA portion, the NASA scientist, to help be part of this bigger effort.
And just curious, that was Antarctic Glaciology, was the NSF program?
No, this was Greenland.
Oh, Greenland.
That was Greenland, sorry. It was a field work in Greenland. Yeah.
Thank you.
Mm-hmm. Yeah.
Just really quickly, just to add to that, I think that what we're trying to do is work together a little bit and make sure we're not paying for the same thing. There's no overlap, but also making sure that we're removing some of the gaps and just making sure nobody falls through the doesn't fit in NASA, doesn't fit in NSF. So we're hoping to work together. We worked together before, so this helps. But, this is good. I think it's, again, moving forward.
Ben?
Yeah, thank you both for being here. I really appreciate it. Thorsten talked a bit about the dual anonymous peer review, and I just want to say thank you. As an early career researcher, it feels very empowering to know that my career stage won't be taken into account and just the merit of the proposal itself. I'm interested, Kelly, if NSF has a philosophy on this or plans or thoughts in general.
So the NASA Cryosphere group was one of the early adopters, and of course our community is in tune with that. So I would say that Office of Polar Programs tends to get asked about this a little bit more than some of the other places around NSF, but this would have to be an NSF-wide thing to the best of my knowledge. Do we have a agency-wide thought on it? I don't know. It's a little above me. As many people in this room know, what we're trying to do is sort of mitigate some of that without necessarily going into dual anonymous. We charge our panelists specifically with reviewing the proposal that's in front of you, and I think the program officer's responsibility is then to make sure that that's what happens in panel. So we're sensitive to it. We're looking out for it. We're charging our panels with that type. And for the most part, I think that has that element. It's not going to be as successful as the dual anonymous, but it's getting us in the right direction. I think we have conversations with our panelists before panel talking about we all have biases. We all have biases. It's just appreciating those and doing everything you can to mitigate what those biases do to you. And, it has to do with being very prepared for panel, reviewing the proposal that's in front of you and giving a specific criteria of why you support it or why you don't support the proposal. And we've hammered that home with our panelists, and I think it has had an effect. It's not at the same level, and I don't know what's to come as far as NSF's policy towards dual anonymous.
Yeah, understood. Thank you for your perspective.
Hi, Kelly, curious, during the moratorium period, do you have an idea of numbers of NSF related, both on the logistics side and on the science side, will be on continent for the next couple of years, scientists as well as staff, and how it compares with a couple of years ago?
That's a good question. I want to adjust the moratorium again.
Yeah.
Again, this was a hiatus on new proposals.
Yes,
We do have active
yes,
stuff going on.
understood.
Let me tell you one of the big pinch points and why, and that's that if we had had a crystal ball way back and saw what was coming on the horizon with respect to the pandemic, would we have made the decision at that point to remove a dorm in the anticipation of building a new one? It probably not. So these two things kind of perfect stormed us. So the pinch point there is we lost a dorm, and then we lose all the beds associated with rebuilding that dorm. I'm confident that we'll make good progress on that in the coming season. It'll give a new number for beds on station. What the breakdown is, I don't know. We still have, infrastructure adjustments that have to be made, specifically at South Pole, and that takes up beds too. What the equation is, I don't know. Do we get back to what we were, prior to the pandemic? Probably. Do we get back to what we were 20 years ago? I don't think so, because now we've got the other pinch point, and that is the fixed wing, especially the LC-130 fleet, which is an aging fleet, and man, those folks work really hard, to help us accommodate science, but it's just a challenge. So yes, 5-6 years ago, maybe not 20 years ago. Is that a fair answer?
Yeah, I mean, it's something, you have generations where there's expansion, and then you reach the end of that life, and so it tends to go in these cycles, and sometimes the different components are not aligned, and sometimes they are. It makes it complicated.
I'm going to let you, this is a good community to talk about this about. The LC-130s have been a challenge, and one of the things that we're doing is adjusting some of our deep field models going into West Antarctica. I think we're going to sort of migrate to a more node type approach, small nodes, and not just very labor intensive, very fuel intensive to go out and set up every year. So we're going to pull a lot of those resources back, either all the way back into McMurdo or at least back to Bird. That's the plan right now. What that will do is, give us, well, first of all, Bird it's 100 miles away and has just a completely different, it's less than 100 miles away, and has a completely different weather pattern. So little things like this to help us get out of that model where you've got hercs just trying all the time to get into a place that's hard to get to, things like that. So we're trying to move into a model that, once we get through the sped space issue, that also takes us into that next generation of trying to figure out how to do this without so many hercs.
I don't think you'll find a group that's more supportive of smaller, more agile field teams than this group here. So that's good to hear. We'll let Gemma have the last question before we go back to the science agenda.
So I'm a postdoc at the University of Washington, which is an institution that doesn't let postdocs have PI status on grants. And I know there are several institutions that have this barrier as well. And that creates this chicken and egg problem where postdocs are trying to get positions, either soft money or hard money, and it's hard to get those positions when you can't bring grants. So I guess I have two questions. The first is, can you clarify whether grants at NASA and NSF are awarded to individuals or institutions?
That's a very good question, because universities handle this differently, just as you said. So it's always, two points. It's always the institution, the Office of Sponsored Program, that submits the proposal, never the PI, right? So if the PI leaves, the university could say, we still will do the work. With the PI, it's not happening. Most people who leave, the institutions send out a relinquishment letter that we need, but the institution owns the grant and submits a proposal. Now, we've come across this problem often enough, and so what happens is we at NASA, we have institutional PI, that's a person who submits the proposal via OPP, or Office of Sponsored Programs. But there's also a science PI, and that can be the postdoc. So then the reviewer the panels realize that who the science PI is, who is actually leading the science. So there's this differentiation between the institutional PI and the science PI, if needs be. And very often what happens is, once the postdoc is not a postdoc anymore, is assistant research scientist or assistant professor or something like this, we can very easily make that change and have that science PI become the institutional PI.
Meaning that the science PI could bring that grant money with them if they moved institutions?
Correct.
Okay.
Correct. So that's certainly a possibility.
But they still have to be a PI, a science PI on the grant.
So there is a PI, an institutional PI, on the grant. On the grant, the science PI is not a PI. There's one PI.
Okay.
Right? But if the postdoc becomes an assistant research scientist or something, we can make a PI transfer, and that person can become easily the PI. It's not a problem. It's something we
Okay,
can,
thanks,
it's
that
on the
helps.
university, it's something we cannot
Yeah.
determine.
Is it similar at NSF?
It's pretty similar, yeah. I think it's pretty straightforward for us to make PI transfers. So I think what you're describing is being a postdoc at one institution, then moving to another institution and wanting to move some of those funds forward.
Yeah.
The flavor of the postdoc, it depends. I think it depends on how, was it a postdoc award or was it you as the postdoc on a regular award, if that makes sense. And we can work through some of those challenges. Nothing is easy, but a lot of things are possible would be the best way the way I would characterize that. And we can talk offline as needed.
Okay, that helps. Thank you.
I will also highlight that NSF forces institutions to accept postdocs as PIs for the OPP postdoc fellowship, which is fantastic. That's like a little lever that you all have to try and enact change at the institutional level, which is very cool. I said we're going to be done, but we got a question online that I think we have to address. So we're going to take 4 more minutes for this. Can you please provide updates about tangible progress NSF is making towards advancing field safety down south, particularly keeping folks safe, working across international contexts in Antarctica? This is especially important during a hiatus when we're being told to go do international field work with our partners when there aren't clear structures for how to handle field safety in those environments.
The clear structures are the challenge. I mean, that's, we recognize that. Tangible stuff. I encourage all of you to tune into when the NSF addresses the National Science Board. Those are public things, so you can Google those and get the schedule, get the calendar, and listen to those, because there's a person in our director's office that has been hired specifically to meet this challenge. Basically, yes, OPP and the Antarctic program in particular highlighted this problem, but this has been escalated all the way to the director's level, and that's a really, really good thing. And a number of FTEs, I think the number is 4 full-time equivalent, so 4 persons have also been budgeted for this effort as well. So that's a really tangible thing, that this is obviously recognized at the director level as a very important thing for our community, but also the science community in general. The second part of that, basically these all scale. I think we brought up the international thing, but we're still, trying to figure out how you go into the deep field with many different institutions and agencies represented. And then that scales to the international. It is extremely challenging when we put people on other people's assets, either stations or boats, and how do we define, what the roles are and how to respond to incidents that happen in those settings. And it's still a challenge. I don't have a great answer. It's not cut and dry. Let me tell you what I think this community can do, though, and that is, I keep pushing the bystander awareness training. If you guys could, the USAP requires it, and that's great, but I feel like it's, driving's another great example. Just because you got your license doesn't mean you're done. It's trying to stay a good driver. And I think the more bystander awareness training you get, the more you kind of keep it in your, keep building that up as a muscle so that you have that dialogue. It allows you to have a good conversation with folks. It allows you to be receptive to it as well. It's one thing to be able to have a nice conversation with somebody and say, hey, I think we could have said that differently. It's also another skill set to be able to receive that. Hey, Kelly, I think you could have said that a lot differently. So keep up with the bystander awareness training. Make sure you're doing it before you go out in the deep field, before you go out on a vessel with foreign operators. Try to encourage them to participate in those once you get on the vessel. Things like that. I think that the way that we move forward is really at that grassroots level, and just build it up in our dialogue, and tell people, basically we're telling the community, this is the community that we want. We want you to be a part of it, but this is what we want. So I think that the international side of things is still challenging. I don't think we've completely figured that out, but I would encourage you folks to give us a little bit of time. Like I said, we've got now, I think, 5 full-time people in the director's office that are trying to address these very challenging issues. Not wholly satisfying, I know, but
So
that's where we're at.
unsurprisingly, you might expect that the very first bullet point in this bullet point list of things that came from last year, the very first one in the lead up to IPY is this international thing, right? The International Polar Year needs this.
Yeah.
And so that's really the challenge right now.
Agreed. Absolutely agreed.
Okay, on that not so positive note, I'm going to pass over to Riley and Emily to convene the next session.
All right, excellent. So we are now going into our session on new software processing and data compilations, which is excellent. We just heard from our program officers both about reusing and better using the assets that we have and have collected, and about thinking about the new stuff that should be coming in the next 5 to 10 years. And so I hope that the 4 folks we have up here presenting today will give you some glimpses into both sides of that. So without further ado, I'll welcome up Thomas Teisberg to kick us off.
Hey everyone. Yes, thank you. So I'm Thomas Teisberg. I'm a graduate student with Dusty Schroeder at Stanford. So yeah, I'll talk a little bit about new instrumentation, as well as some thoughts on how at least the data we collect with those new instruments can be better reused. I'm actually an electrical engineering PhD student, so thank you all for welcoming me into your community for so many years. And for the last 4 years or so, I work together with Anna Broom, who's another electrical engineer in our group who since graduated, on building these software-defined radio-based radar systems that are really flexible, relatively low cost, easily reconfigurable. And we've used these to create sort of this architecture that we can use to rapidly create new instruments, as well as make it possible for other people and other groups to recreate some of the instruments that we have developed and deploy them for their own purposes. So my goal today is I'm going to talk a little bit about 3 of the 4 ice penetrating radar instruments that we have built in our group and deployed in various places, and along that journey give you a flavor of what systems you can build with the capabilities in the Open Radar Code Architecture, or ORCA as we're now calling it. And then at the end I'll point you to resources for how you can find documentation to either build some of our systems or think about how you could leverage the work that we've done to build customized instruments that are perfectly suited for whatever you're trying to do. So to get started with that, just to give you a brief idea of what the architecture of these systems is, when we talk about a software-defined radar, this is sort of the core of what we mean. So we're going to have some host computer, that could be your laptop, it could be a Raspberry Pi, anything in between, that's going to talk to a software-defined radio. And a software-defined radio, or SDR, is basically just a flexible platform for building any kind of radio frequency system where a lot of the parameters that would have been set previously in the way you develop the customized hardware is instead designed to be incredibly flexible and reconfigurable in the hardware, and then that complexity is moved into the software. So the ORCA system that we built is fundamentally a set of code that runs on this host computer and talks to the software-defined radio and basically runs that software-defined radio as a radar with customizations for the types of radars that we build in this community, by which I mean ice penetrating radars, but I don't exclusively mean deep sounding necessarily, like any of the types of sort of nadir-looking systems that we use to look through ice, whether the goal is to look into the ice or beneath the ice or what have you. Beyond a computer and an SDR, the simplest version of this is just those things plus a transmit and receive antenna. And some of our systems are truly that simple. Depending on what you are trying to achieve, you might also be adding a power amplifier if you need more power than the SDR you picked can put out, or any number of possible RF front-end components, filters, low noise amplifiers, attenuators, that sort of thing. And the really nice thing about the way that this system is built is that at the core of our system is a single YAML file that defines all of the parameters of both the radar system that you built and the data collection that you're going to do. So that single file that's this human-readable text format incorporates things like the center frequency you're going to use, the bandwidth, the type of chirp, windowing functions, timing parameters, et cetera, et cetera. And getting to the reuse part, that's one of the beauties of this system. I'm going to show 3 very different radar systems, but they're all built around the same code. The only software difference between them is this one YAML file. And every time you do a data collection, the details of this configuration are saved with your data. When you get into our post-processing code, it reads that same configuration file and then automatically knows how to post-process this data. And that has also allowed us to intercompare data collected with different systems in some really cool ways, because we have saved with each data collection a lot of the metadata that you need in order to make comparisons between data that you've collected. So the main system that I've worked on is Peregrine, which is a UAV-borne radar system. And the core of that is this Peregrine radar payload. It's a super small box, is about this big. I should have brought one with me, but weighs less than 350 grams. And it basically incorporates a Raspberry Pi as your host computer, a few interface electronics, and then an EDIS B205 Mini, which is the lightest, lowest cost SDR that the EDIS series has available. We use that primarily, or was originally built to be the payload for Peregrine, which is this 2-meter wingspan fixed-wing UAV. We now have some of the instructions to build this, and if you're interested in using it, you can talk to us. We do have a couple units available. But this is basically, as you can see in this, over a series of pre-programmed waypoints, and then lands back on the Glacier with you, and you can download the data. This is designed to be a very light field portable system. To give you an idea of how this can be useful, I want to show you an example of some field work we did a couple years ago now on the Slackgreen Glacier in Svalbard. As you can not really see from this imagery on the projector screen, it's a heavily crevassed glacier. So there was just one flagged route that we could actually traverse along here. But what we were able to do with the peregrine system is we were able to traverse along the flagged route and then fly the peregrine system out onto the margins where we weren't able to safely go as humans, but we could send our UAV out and collect data there. So over the course of a few days, we did about almost 60 kilometers of airborne surveying, all out of one Pelican case. A lot of the way we visualize this data now is in these like film strip visualizations where we take a radargram and we kind of wrap it with the path of the flight line. This was built for us by a mountaineer on a snowy day with no internet, which is amazing. But you can see here, you can see the the bottom of the valley here, and then the ice surface up here, and you can see the topography of the glacier, the bottom really well. Looking a bit higher up the glacier, you can still see the bed as well. Surface is up here, and then what's really cool is you can actually see this, what we think is this transition layer, where the top is cold ice and the bottom is temperate ice. This is very characteristic of a lot of Svalbard's polythermal glaciers. And the beautiful thing is this system is super lightweight. So this packs down to a single Pelican case plus a tripod and a laptop. So very logistically lightweight to bring out and use. It can actually get even simpler than this. So this is a system, this Pelican case is like this big, that Danny May, who's here in the audience with us, built with us. And over the course of he was interested in doing multi-off-static bistatic surveys, and so he wanted to use our system as a passive receiver to listen to a PRES and then have a whole bunch of these as wireless receivers that could be synchronized in post-processing. So you'll see that's the same Peregrine payload box, some different low noise amplifiers, and then the rest of this case is just batteries. In about 3 months, we went from concept with this to building 5 of these, 4 of which Danny and Paul Summers took to the field, and this actually worked. They were able to collect this multi-offset data in a common midpoint survey style, where you can see the direct path as well as these glacial reflections on an ice shelf in Antarctica. Sometimes you do need more capabilities than what's offered by that tiny little box in that 50-gram SDR. So everything I've showed you so far is with the B205 Mini, which, as you can see, weighs almost nothing and only costs about $1,500, but it only gives you 56 megahertz of bandwidth and a single channel. So Anna Broom, who I mentioned, built this system with me. Her primary project was a multi-frequency radar radiometer system, so she needed more bandwidth and more channels. So she went up to the X310, which, as you can see, costs an order of magnitude more. But then you can build these really cool systems that have these huge high-power amplifiers, some more complicated front-end componentry. But you can see this is all sort of the same pieces put together, and it runs exactly the same code. You can pick any SDR in this family and run the exact same code on it. This is example data, which you absolutely cannot see, I imagine, from back there, but you can take my word for it that this shows the profile of the bed at about 3.1 kilometers beneath the surface. This was done just west of Summit Station in Greenland, sorry, not Antarctica. And you can see what the system actually looks like here with these huge super wideband antennas being towed behind a sled. So all of these systems we have, they all run on exactly the same code. The only difference is that one YAML configuration file. They all use the same post-processing to generate all of the radargrams and results figures and whatnot that you have. You can find instructions for sort of basics of how to build these things, what the bill of materials are, either done or work in progress on our website. You'll also find here sort of suggestions and resources for if you're trying to build an instrument and you want to base it on this, how would you get started picking components, picking which SDR you're going to use, those sorts of things. I will say that a lot of these bits of documentation are works in progress. So if you are interested in building one of our systems and deploying it, or you're interested in developing an instrument based on some of this or whatever, please get in touch with us, and that can either spur us to finish up pieces of documentation that you might need, or help you out in whatever other ways. So thank you for listening. We have our project website. It was orca.radioglaciology.com, and then you can also take a look at our paper that just came out if you want to dive in the nitty-gritties of how these things actually work. And please feel free to email any of us or find myself or Danny at this conference.
Thanks, Thomas. That was awesome. A reminder that Thomas is a student, so please scan the QR codes to give him feedback. And our next talk will be by Ben Hills, who's going to be telling us about radio stratigraphy.
We'll see if I can figure out the. Nope, that is not. Okay, yeah, we'll give it a try. Okay, so I will start by just thanking a few people. Some of this work is built upon past work, especially coming out of the Stanford radio glaciology group. So I'm going to call out Davide and Dusty both, but I'll kind of talk through a little bit about what they did and how it informed some of the way that I think about some of these things. Lots of different institutions. I did add an NSF logo also to this last minute, but I didn't make it to the version, so just pretend that there's an NSF logo up here. They're funding me. Yeah, so thank you to them as well. I'm a Mines postdoc, if I haven't already introduced myself. So my talk within this session is about data processing. So not so much about science. The location here doesn't really matter, but started with Thwaites Glacier because this meeting tends to think about Thwaites a lot, and it's an area that folks will be familiar with. Unfortunately, all of my images are going to use the same color scale that Thomas used, so you can't see it super well. But for folks who don't think about radar a lot, you can see, you know, the ice bed interface here, and then what I'm more interested in is all these layers from within the ice column here. So a little contrast, thank you, little contrast in dust or chemical contrast within the ice create these reflections, and those can be used to kind of date layers across the ice sheet that might be useful for understanding dating ice cores, things like that. What you can see here, or maybe not see very well, are these disruptions in the layers. So I'm going to point out two. There's one kind of right here that I'll show on another slide that you'll be able to see a little bit better. That's a horizontal disruption that's from a birefringent effect. I'm interested in that, and some folks will know based on talks at prior WAIS conferences that I'm interested in kind of the birefringent effects that we see in ice. But then this talk, I'm going to talk more about the vertical disruption, so these ones here, and I'll talk about where each of them come from. So if you want to learn more about the birefringence and this beat signature, I encourage you to go check out Lucas's poster. He did a nice job introducing some of that material and what we're thinking about from the polar gap survey this morning. And then, yeah, I'm going to talk about these, which I argue are a processing artifact. So these show up all over the place. Here you can see the beat signature a lot better from this figure that T.J. Young published a few years ago. All different radar systems, all over Antarctica and Greenland for that matter too. You see this kind of horizontal disruption in the radio stratigraphy, and that's because of the way that a polarized wave interacts with anisotropic ice. Same thing's true for these vertical layer disruptions. All different systems, all different places throughout Antarctica, those show up. And I'll just kind of briefly, 101, talk about why this happens. It's because we process with a synthetic aperture, so stacking across multiple traces in different ways. So the ways that you might think about the products that are available, for instance, from the Croesus server, you might have a horizontal stack, just kind of averaging the traces together, perfectly horizontal. That would be like the Croesus Quick Look product, kind of just something that's quickly processed, not necessarily meant to be used as a final product. But then the standard SAR focusing product might stack kind of along a hyperbola. And in either of those cases, when you're trying to line up the waveforms, there might be some destructive interference when the layer is dipping. So if the layer is flat, then you get a nice stack in the horizontal. If the layer is dipping, then you're kind of stacking across them, and that's where you get that destructive interference. So, yeah, this is unfortunate. So, if people are interested in looking at the images, come bother me after. So the raw image here is just pulse compressed data, and then you might be able to make out that here we have the destructive interference here, and this is for nadir focused data. So this would be just with the synthetic aperture pointed straight down, and the radar instrument looking straight down. This is the kind of standard focusing. What you might be able to do instead is, this is what Davide came up with, and it is based on some work that Nicole Shu did as well. thinking about how you might be able to, if you know what the dip angle is, that you might be able to just stack along that dip angle and then recover those, the signal within those dipping areas. So, and what's critical here is that you know something about the dip angle so that you can get at that. And I'll talk kind of closer to the end of my talk about how we might be able to extract that. Yeah, in this case, you'll have to believe me that the stratigraphy does get recovered, and this was just kind of reproducing what Davide had done there for this location that I have from Academy Glacier. But the trade-off here is that you're kind of sacrificing the strengths of the focusing, where you get really good resolution and you kind of recover or you resolve the diffuse echoes kind of at the bed, and you trade that off for being able to see signal within the dipping stratigraphy. What I am proposing, and I've been thinking about a little bit, Davide's algorithm made me think about how the SAR community, like the spaceborne SAR community, sometimes processes with what's called a squint angle, so that's having the radar antenna looking forward. So if the actual physical beam pattern is looking forward relative to the trajectory of the instrument, then you might process it with this squint angle, and how that comes into the math is with a linear addition. So the quadratic term here is an approximation of this shape, the curvature, and then if you process with a squint angle, it has a linear term as well. And what you can think about here is there's these two components that I was talking about before, the kind of focused, the traditionally focused, and then the low SAR is much more like this linear term. And what I'm going to propose is we can kind of take advantages of both. And I started thinking about this and then eventually realized that there was an old IGARS abstract that's kind of buried and has barely been cited, I think 2 times, from Prasad's group. So they thought about this a while ago as well. So what you can do, and I promise that it does look okay, you can kind of make it out near the surface, is that if you process with different squint angles, then different stratigraphy shows back up, and you can recover those angles. Or you can recover the signal within those dips. Yeah, I'll let it play a couple times if you can make anything out there. So if you're looking straight down, then the dipping reflectors might not show up, but if you're looking kind of at an angle, then you can recover those. So what we need to do, if we want to kind of compile those into something of a mosaic, then we need to know what the dip angle is at every location. So what you do in that case is, for each location kind of moving along the track here, we can do some frequency analysis. And what you expect is that because of the Doppler effect, that you kind of get a shift down in frequencies for layers that you're moving away from. So if the plane is flying in one direction and you're actually getting echoes from behind you, then you get frequencies downshifted. And if the echoes are coming from in front of you, then the frequencies might be upshifted. And that's what I'm showing here on the right. And so we can recover those dip angles and then use that to kind of compile a multi-squint image, if that makes sense. There's also some information about the specularity of the reflections within this. So if you kind of get like a really sharp return at one point, then that layer is highly specular. And that's true for these in-glacial echoes here near the top. And then if you get kind of the energy spread across this hyperbola, then the energy is, or the reflector is more diffuse. So one of my interests, and this is something I'm working with Hannah on at Colorado School of Mines, is actually using these products here. So not just kind of reprocessing the image to recover the layers, but actually using what comes out of this processing algorithm as signal rather than something to be corrected for. So the layer dip is quite interesting in terms of the ice dynamics, especially if you have a flat bed and the layers are still dipping in ways. That means that either there's been some kind of accumulation history that's interesting, or that the ice dynamics are changing in some way. So you imagine that if you have like a strong shear or maybe longitudinal extension, then the layers have to dip to accommodate that. Same thing for the specularity. Hannah is doing a lot of interesting work thinking about the bed echo, but ultimately we want to think about how the signals that she's seeing in the bed echo might correlate to some of these signals that we're seeing in the internals as well, both the dip angle and the specularity. Okay, the final image, you'll have to come look on my computer, but it does look a bit better, and I think it's an interesting compromise between this low-SAR algorithm. So I'm really interested in these disruptions within the radio stratigraphy and what they can tell us in terms of signals for ice sheet history, ice flow, ice dynamics, and we can get at a lot of this, especially if kind of like some of the lower level radar data products are posted. So oftentimes, the like focused product will be posted, for instance, on the Croesus server, but then you need to kind of go and like search for these lower level radar products in order to do more sophisticated analysis. So I'm interested in kind of getting some of that data posted so that more and more people can do these types of analyses. Thank you.
All right, so our next speaker will be Sophie Anderson. All right, I apologize. I don't know anything about Macs. Where's the file folder live? Someone come save me. Naturally, it's the smiley face for the rest of you Windows people out there. All right, now Sophie, please, and remember to vote for her. She's a student.
Okay, hi everyone. My name is Sophie. I'm a fourth-year PhD student at the University of Colorado. And my presentation today nominally is on the effect of weather events on GNSS reflected signal coherence, but I'll spend the first half of the talk talking about what that is and why it's useful for ice sheets and ice shelves at all. So for those of you who are not familiar with GNSS reflectometry, it's a multi-static radar system where GNSS navigation satellites, like the GPS satellites, act as the transmitter. Those signals are available everywhere on Earth, and they reflect off Earth's surface and can then be received in low Earth orbit by a different constellation of satellites. And then by processing those reflected signals, you can tell some geophysical information about the reflection surface. So this is something that is used often for ocean wind speed retrieval or soil moisture retrieval, but it's pretty early stage for cryosphere applications. So I'm working on extending it to applications for the Antarctic ice sheet. So why might we do this? Relative to in situ or airborne and other spaceborne remote sensing platforms, this method has really excellent spatial coverage. The GPS and other GNSS systems are designed specifically to be available everywhere all the time, so the reflections are also available everywhere all the time. The receivers you need to receive this type of data are pretty cheap and can just be easily launched into low Earth orbit. But the disadvantages come from the fact that we don't actually have any control over the transmitted signal. So these signals are really weak, and we're just looking at what's available. It's an opportunistic method. So I have been looking at this data set that you can see there on the right. It's from Spire Global, which is a commercial satellite constellation. And they have a constellation of satellites in low Earth orbit that have side-looking receivers. So that the antennas are looking toward the side and receiving reflections that are occurring at very low grazing angles of 5 to 30 degrees off the surface. This is the data volume that I'm looking at in a 3-year period from 2021 to 2023. And this shows at 10-kilometer resolution how many samples I have over Antarctica. So I'll spend a little bit of time talking about how I've used this data over the past year or so. So for those of you who are familiar with navigation signals, usually these GPS signals consist of a binary code that has a bunch of navigation information that's modulated onto a sinusoidal carrier wave. So here I'm dealing with the sinusoidal carrier wave rather than the navigation information. And I use this phase coherence term, which is a measure of the phase continuity of the carrier phase. So this is a quantitative metric to determine whether a reflection was specular or not specular. And you can imagine, I guess many of you are probably familiar with that concept, but you can imagine that if there's a very smooth surface, the reflected signal will appear pretty similar to the transmitted GNSS signal, whereas if there's a rough surface, you'll get an incoherent reflection. So I won't spend too much time here, but you can see on the top right plots there, there's an example of an incoherent and a coherent segment, which are notated on the bottom 2 plots with the gray and red intervals. for those segments, you can see that the residual phase, which is the observable I work with, in the incoherent segment, sort of in the center there, is just basically noise. It's all over the place, whereas in the coherent example, that phase looks pretty linear and as you would expect for a perfect sinusoidal signal. So this phase coherence metric is very closely related to surface scattering, so it depends on all of the variables you might expect, like frequency, elevation angle, but also on surface roughness. So I processed a large volume of data over Antarctica and gridded it in various resolutions. So this data represents the phase coherence of all of the signals in each grid cell. So the left-hand plot is for Antarctica, and you can see, let's see if I can get this. So you can see a few important features. One, you can see that the sea ice is more coherent. Dark, in this case, is more coherent, so that means a more smooth surface. So sea ice is known to be more coherent than the ocean surface, so you can see sea ice extent. It's a little hard to see, but there's also some features in the interior of the ice sheet, and then it's really clear that in the ice shelves, there are more detailed features. So the right-hand plot is Ross Ice Shelf at 3-kilometer resolution. Again, I'll point out some features. You can see a very clear boundary between the sea ice and the ice shelf surface. That's because the sea ice is smoother, so it appears more coherent. You can see flow stripes over here pretty clearly, and then a few large open rifts in the ice. I have a paper on this that's in the review process right now, so be on the lookout for that if you're interested, but I did some more work kind of quantitatively comparing this to a roughness data set derived from the reference elevation model of Antarctica. But for now, I'll just show a few more examples. So this is the Ron-Filchner ice shelf, and then on the right, this is the Wilkins ice shelf, which I have a little map up here that's in the Antarctic Peninsula area. These are at the same resolution, but Wilkins ice shelf is just much smaller. And both of these I have a little bit more to show, so I wanted to introduce them. So I have a kind of anecdotal result here. As many of you know, I'm sure there was a major calving event in May 2021 from Ron Ice Shelf, where this is a Sentinel-1 visual image, but this iceberg is larger than Rhode Island, and it calved off in May 2021. And I thought that this was likely to be something I could see in the GNSSR data. So I used all of the data in this top plot from 2021 from January to May, so before that calving event happened. And this is at 5-kilometer resolution, and you can see that there's a 2020 coastline and a 2022 coastline. So it's a little hard to tell what's going on, but basically this area up here, that's the sea ice, and that's more coherent than the ice shelf down here. And then in the bottom plot, that's all the data from after the calving event occurred, so also the same resolution, but now you can see that the ice shelf boundary really clearly matches up with the 2022 coastline, which shows that now that iceberg has calved off and the sea ice is very coherent, so it's a pretty obvious result. So this was just an interesting anecdotal example. But now for the portion of the presentation that corresponds to the name. I've been working on seeing if this is something that we could extend to look at more shorter timescale events where I'm not averaging 3 years of data, but instead I'm just looking at data before and after a storm. So I chose the Wilkins ice shelf as a case study region because I know that's an area where there's more extreme weather to look at. So I pulled some ERA5 reanalysis data for this area where I have snowfall in the top row there and then snow melt in the second to top row. And I don't pay too much attention to these plots, but basically the takeaway here is that I also have coherence in this row of the plot. And the takeaway is that I didn't see any clear relationship between the weather events and the coherence. I did do a little bit more statistical analysis and kind of more comparisons than this, but this shows a 5-day average of coherence versus those variables, and yeah, there's very little correlation. And I think that the reason for that is that GNSSR data is fairly noisy and especially when you're not averaging a large amount of data. The noise and then also the fact that it's very related to all of these other parameters like satellite geometry and receiver antennas even play a bigger role when you're looking at fewer data points. So I did a little bit more work recently just trying to analyze where the main contributors to this data are coming from. So I took this is a month of data And then I took all of the points at which two tracks intersect, and I was trying to analyze the difference in coherence at intersection points versus the difference in other variables. So in this top plot up here, the y-axis is the difference in coherence between two tracks at the point where they intersect. And then the x-axis is the number of days between the measurements. And so you can see that there's very little relationship between these two variables, and what that tells me is that at least at the level of fidelity that I'm seeing now, because there's no relationship in time between the difference in coherence and the amount of days between the measurements, I think that I need to correct many other parameters before I can go looking in a confident way at whether there is more relationship with elevation angle and azimuth angle of the measurements, which is something that we expect, and that's something that I'm currently working on correcting for, so that I can have a little bit more confidence in individual measurements when I'm not averaging over such a long time period. But in summary, this is a really early stage technology, and I'm excited about the potential for it to complement other data sources and hopefully provide some surface roughness and eventually surface elevation measurements, and more work is required, which I'm currently doing to isolate the effect of each of these measurement parameters. So thanks for listening.
Can I ask a question? Awesome talk. I don't know much about this subject, but on your map of continental coherence, it looked like there was high coherence over the subglacial lakes. Yeah. Why do you think that is?
Where, can you point out where?
In the middle of East Antarctica. That looks like, I mean, maybe it's not, but that looks like a map of a lot of like kind of radar, classic radar detected lakes.
Yeah, I think that I haven't done a lot of work with that yet. It's possible. Something that's on my to-do list is to look at the penetration depth of this. It's L-band signals. So in theory, there could be some penetration depth. They're at really shallow grazing angles. So I've been operating on the assumption that they are scattering off the surface, not anything under the surface.
So
it's
maybe
possible that there's something under the surface, but I think that my theory about what's causing this, and it doesn't look quite right on the screen there, is just that it's topography. Like I think those areas where it's more coherent are just, they have much less change in elevation.
Got flat topography.
Flat
of the
topography.
lakes.
So I think that's why, and I guess that maybe would correspond with the locations of lakes too, but that's my kind of going theory, but definitely more work is required.
Yeah, cool, thank you.
Thanks.
Awesome, thank you, Sophie. Reminder, Sophie is a student, so please give her feedback. And so is our last presenter for this session, Eric, who's going to talk to us about using cryosat to fill in the gaps between ISAT and ISAT-2. I don't know. No, just full screen.
Okay, thank you. Greetings, everyone. My name is Eric Kabe, and I'm a geostatistician actually right now, PhD student at the University of Buffalo. And this work that I'm about to present is part of my research, which is multi-sensor altimeter data fusion. So it's a pleasure for me to have this opportunity to share my work within the broader community. So the ice streams in the Cyprus coast have experienced a complex trend of surface variation. At least this is what previous work were able to show. And not only that they are complex, but also if you look at the change rate of that trend in time, it's nonlinear. So basically, if you look at the trend of the surface elevation change during the ISAT period, it's going to be different than the one that you have when you look at the trend during the ISAT-2 period for some locations in that area. So we have like a 9-year gap between those two missions, and neither ISAT or ISAT-2 can tell you what's going on in the Cyprus coast. So an example here is if you look at this plot with the different time series collected at those different locations, look at the red graph, for example, the MIS2, you will see that during the ISAT period, it's kind of flat, so it's literally like slipping. And during the ISAT-2 period, we have that location gaining mass. So without any information between those So if the gap is an issue, then how to fix it? Well, one idea is to bring in CROSAT-2 to fill that gap. And we know this is also particularly important for folks that are working on subglacial lakes monitoring, because oftentimes they use the surface flatness to infer presence and/or dynamics of subglacial lakes. So if we have enough data in between, so if you have enough data to fill the gap, we can help them improving their job. But the problem with radar wave is that they can penetrate the ice sheet surface because of the frequency used by CROSAT-2. So CROSAT-2 is using a radar altimeter, and over dry condition, the radar signal can penetrate the surface. And so we'll have surface scattering and volume scattering, which brings a bias within the surface elevation measured by the sensor. So that ice penetration has been documented in the literature, and you will see that some papers will mention that it's not that much, so it's not that big. It's maybe like 0.3 to 5 meters below the surface. And there are some other documents that will mention a penetration of about 10 meters. So it's a big deal. We need to have a proper way to quantify that penetration before we merge CROSAT-2 with ISAT and ISAT-2. So the CROSAT-2 data that we're using is from Nielsen et al. 2022, where they produced a long-term reconstruction of the Antarctic ice sheet. And the surface estimate is a guess of the surface elevation using ISAT and ISAT-2 at the locations that we have from CROSAT-2. And to have those surface estimates, we use geostatistical predictions or geostatistical estimations. One of the essential part of using geostatistical algorithms is how we select the type of random function that we want to implement into our algorithm. So usually, if we run, for example, simple kriging or ordinary kriging, either if it's only just the simple kriging or within a sequential Gaussian simulation, we will use the hypothesis that the random function is a second-order stationary function. And sometimes it will work, but sometimes I just might have to switch to a higher order of random function, which is, in this case, a sort of generalized type of random function called the kth-order intrinsic functions. So they are both used the same way. And the only difference is going to be the components of each system. So in this case, for example, we can have the gamma and k that are different. For second-order stationary function, gamma is a semi-variogram, but for the kth-order intrinsic function, gamma is like a kth-order variogram, which is different to a semi-variogram. So a semi-variogram is simply a function that we use to quantify the difference between the observation separated by the lag distance. In this case, we are in the spatial temporal domain, so we have 2 points in space and time, and we study how different they are when we look at the surface elevations. So we quantify that value using the semi-variogram, and it gives us a trend of spatial temporal variability that we can use to mimic surface elevation at the locations that where we don't have the original inputs or original raw measurements. And so the idea is to use the corrected surface elevation from CROSAT-2 and merge them with ISAT and ISAT-2 so that we can produce a final gap-filled time series that we can use now for further analysis. And over here, I'm just showing like an example that we have from the tool I'm developing for my research. So you will have the final time series, but you will also have the chart showing the correction that you applied in order to have the final time series. And another graph just to show you the trend of surface elevation in time within a location that we will call a patch. So the the algorithm that we built has been implemented on 3 sites in the Cyprus coast. The PPT-15, which is near the MIS-2 on the Mercer Stream, the Willenstrong, and the MIS-2, again on the Mercer ice stream. And the idea, again, is just to test those different type of function and make sure that we can design a way in which the tool will determine which type of function is appropriate for the work that we want to do, like producing the time series. So this is how the framework will work. We have a patch in which we collect the raw data. And those data are coming from each sensor, so we bring them all within that patch. And what we do is, one of the sensors is going to be the target, so that's the one that we want to correct, and the remaining one will be the conditioning data. So that's the one that we use to correct the target. Then we have estimates of surface elevation with the location from CursAT 2, and we apply that correction on the original data from CursAT 2, and we merge them together to produce the gap-fill time series. And this is a visual description of a patch. So basically, it's like a cubic object in which we have the surface elevation measured by different machines or different sensors. And within that cube, we try to reconstruct a time series. So it's like basically how the surface elevation is changing within that cube in time. But we use the measurement that was collected in space and time. So because all of them are measuring a specific location at a specific time, they are not all measuring the surface at the same time. So over here, we were able to have a correction for the PPT-15. And what we have to focus on in this is how good are we reproducing the trend of the surface elevation versus time plot? Because if we are not able to reproduce that trend, then we need to improve the algorithm. And the second point is, do we have local variability between ISAT 2 and CursAT 2 at a specific point? Because if we have that local variability, then it can conduct to misinterpretation. Maybe someone would think this is a rough point at the surface, but actually it's not roughness, but it's just that artificial noise that we need to correct caused by the ice penetration. And so we applied the framework on the different location near the Wind Strong. And this one, for example, is where we think there's a limitation within the algorithm, because now when you want to compute the time series, you want to grab some neighboring information around the point where you compute. And if that process is not strong enough, it will just grab a specific set of points. And because of that, you can have this type of feature where you think maybe there is a flat, slipping glacier flowing over there, but actually it's not that. It's not the case, but it's just because of the points that we collected. Because if you look at CursAT 2 over here, CursAT 2 is flat, but ISAT 2 is changing. So maybe grabbing only CursAT 2 would impact the response in this location. So which is one point that we need to improve. But again, remember that another goal is to test the different type of random functions to use. So in this plot, for example, we have a test where we compare second-order stationary function with k-order intrinsic random functions. So the red is going to be the second-order stationary function response, which is when we use ordinary Kriging plus Bayesian inference to guess the best estimate of surface elevation for that time series. And the yellow one is going to be the solution where we use a k-order intrinsic Kriging plus Bayesian inference to get the best estimate of surface elevation at one location. So if you look at this one, well, red and yellow, they are relatively good, not that bad, especially during the ISAT 2 and ISAT period. And over here, the red curve is a little bit unstable or irregular. But then we go to the next one, and then we see that even during the ISAT period, the red solution is unstable. And this is actually worse when we look at the third solution, where the yellow response is still stable, but the red one is unstable. So with this, we understand that selecting the appropriate type of random function is crucial if you want to process the data within the patch, either for reconstruction or for interpolations. And yeah, we have been able at least to fill the gap, to have an understanding of how the surface elevations are changing during that period where we had no observations before, and now we can tell at least what's going on between that period of time. And so the next step is now to implement this framework within the larger fusion framework that I'm building. and use the fused data set to produce the gridded data of ice sheets topography at different time epoch. So it's, what I'm trying to say here is usually people will use geophysical correction to address the ice penetration problem. But we can also use other missions like ISAT and ISAT-2, which are laser altimeter, because we know that they are less sensitive to ice penetration. So if we have the measurement from ISAT and ISAT-2 and CROSAT-2 at the same location, we can just study the offset and use that as an estimate of the penetration caused by the bias caused by ice penetration. Another thing is we are using geophysical simulations, and sometimes if you have a big data set, it can take a long time to compute. But we know that there are publications out there addressing that problem, especially using parallel computing. So that's something also we can implement and also work on addressing the information effect. And now, by processing all those time series and making the gap field reconstruction of surface elevation in the hypercourse, we have the opportunity to provide those data sets to those who are studying subglacial lakes, and maybe now they will have a better understanding of what's going on for the specific location or the specific lake that they are studying. So I would like to thank everyone for the attention, and yeah, if there are questions, I'll be more than happy to answer them.
All right, I'd like to invite all of our speakers from this session back up to the table. We're a bit behind on the schedule since we took some extra time with the program manager, so unless Matt stops me, I might eat a few minutes into your break so we have time to question folks. All right, we'll go till 3:20. Matt has given me sanction. So come with all of your questions. We have time. Surely they have not solved all of our problems yet. You have things you want to ask.
This isn't quite a question, but it's a good opportunity to kind of talk about, there's an American Drone Act, and I'm sorry, Thomas, your presentation just gave me the sort of, this might be the best time to talk about it, but we're no longer allowed to use certain components from various countries. There's kind of a list of things we shouldn't use anymore, and a list of what they call the blue list, or drones and drone components that could be used. So if you guys have any questions on that, please reach out and we can kind of point you in the right direction. But sorry, this session gave the best opportunity today to kind of address that. Sorry, not a question.
Yeah, to add that, I think Raspberry Pi is safe. So my question was for you, Thomas. Just to talk to us about the battery that you use. Like, I know, like, being in a field, weight is important, and batteries are usually the heaviest thing in a piece of equipment. So what kind of battery do you use, and have you tested using like different types of batteries that are lighter?
Yeah. Okay. So for the Peregrine system, we use lithium polymer batteries. Actually, well, we actually just switched to lithium-ion batteries now. So we're at lithium-ion batteries on the UAV. In the context of the UAV, not by accident, the UAV is made of a foam material that's a pretty good insulator. So the excess heat inevitably generated by the radar system keeps the batteries nice and toasty. It stays at about room temperature. For the ground-based systems that you saw, like MAPR and IS, the other two systems, those systems use lead-acid batteries.
So we were talking about estuaries earlier today, sub-ice estuaries, and it seems like some of the radar tools we talked about today, particularly a drone with some clever processing, seems like. What do you think, again, Thomas, what do you think and probably Ben's perspective would be helpful here too, what do you think the promise of this is? Like how much of an estuary of the size or seawater intrusion of the size Alex was talking about can we map, and on what sorts of temporal frequencies?
Yeah, so I guess my view on this is that what we really need to get at some of these processes, and obviously I'm biased here, but is high resolution time series data, and that in some contexts the time series, which is largely what we've been missing because we've been looking at ice penetrating radar as a one-off mapping game, but actually even if we sacrifice spatial resolution, in a lot of cases if we had or I guess low frequency temporal repeats, so we got like high time resolution, that would really help answer this. I think what we need to get to in order to make that happen is we need to figure out how to operationalize some of these UAV measurements much better, because right now the only way that we tend to effectively get time series is by putting a satellite up where it's in a repeating orbit, and then we get that time series over and over again. Right now, basically every UAV measurement ever made, most airborne measurements are, with some exceptions, and Icebridge did a good job of this, have very few repeats, so it's very hard to get to that temporal thing. Drones could give us a way of having essentially automatic repeats where we say we're going to make this measurement and we're going to commit up front to making this measurement, every month for the next year or every year for the next decade or whatever. And we need to figure out how to operationalize those kinds of measurements and figure out how to do the data processing and data availability for that. Do you want?
I don't know that I have much brilliant to add. I think that time series analysis is really interesting, and definitely we should be flying repeat flights for all sorts of different reasons. I might actually add another question to Matt's question, that sometimes some of the areas that we might be really interested in and are hard to get to from a logistics perspective are also hard to measure things. So like in a crevasse region, you might get a lot of surface clutter. And I'm interested in whether you've thought about, or like if you see a lot of that in the survey that you did up in the Arctic, or like if you have mitigation strategies for surface clutter in particular.
Yeah. I mean, again, so basically the two things that you can, or the three things you can do for surface clutter are you can improve your antenna beam pattern. That's two parts. One is by having a more directional antenna, or by flying a giant grid and doing synthetic aperture focusing. But ideally you need not just a long track, but like you need lots of closely spaced lines, or flying lower where you see less of that surface clutter for the same antenna. So the UAVs are really great because you can safely fly very close to the surface, and that just automatically suppresses a ton of surface clutter. Or if you're not going to do that, then the alternative approach basically is to do tons and tons of really dense gridded surveys. But when I say dense for this purpose, I mean like meters apart in flight line, like things that are relative to the wavelength, much, 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 much denser than anything we otherwise talk about most of the time.
Go for it, Ellie. Great talks, everyone. Thank you. It was really interesting. My question is for Sophie in particular. You showed how there is this really clear difference in coherence between sea ice and the ice shelf. Do you see similar differences in coherence between sea ice and open ocean?
Yeah, that's a good question, and the answer is yes. I think sea ice is a more developed application than land ice with GNSSR, so there are a good number of people who have been able to map sea ice extent and even sea ice age using this coherence metric, because first year sea ice tends to be much flatter than multi-year sea ice. So yes, so the answer is you can pretty easily see the difference between sea ice and open ocean. Yeah, and it is effective for extent. The spatial resolution is on the order of a few kilometers, so that does limit certain applications. So yes, but the answer is yes.
Yeah, I guess to follow up then, are you able to monitor around the year? It seems that you're capable of monitoring in polar night as well.
Yeah, it's year-round, all day, all weather. Yeah.
And so you can see like open features in the ice. That's really cool. Okay, awesome.
Yeah, if they're big enough, yes. Yeah.
question for Eric. It's fun to see a geostatistics talk. Are you interpolating like 1D through time or like 3D through space and time?
That's a good question. So in the patch that we are analyzing, we have the data distributed in space and time. But we can focus our interpolation in the center line going through that cubic object and project all the points on that line for the interpolation.
So you can, so when you're interpolating through time, you're still able to like consider that two grid cells near each other should be changing similarly, or are they unrelated?
Yeah, similarly, kind of.
Would it be easier to like interpolate the thickness change rather than interpolate elevation, like just change the variable you're interpolating?
Yes, that's an issue actually, because most of the work that you will see in the literature, they're actually using elevation change instead of raw elevations, just because the size of the amplitude of variation is big with those raw data. But then if you tune up the Kriging algorithm, it can handle that problem so that you don't have to work on the residual data, but actually the raw initial data.
Cool, thank you.
So I have a quick question for Sophie. I really like your roughness map, and just in optical imagery, it's often difficult to distinguish rifts from surface expression of basal crevasses. For example, it's hard to distinguish different crevasse feature. And it seems like in your roughness map, you can clearly see rifts, right? So I was wondering if that's if you thought about mapping rift using your data product, or even suture zones. It seems like you can see that in your map as well.
Yeah, that's a, so I did some more work on like trying to figure out exactly what I was seeing. And there was a really great paper from 2017 that identified structural provinces on Ross Ice Shelf. And so I did try to compare the like zones I was seeing of high and low coherence to structural provinces that had similar deformation, that indicated a similar deformation history. And it matched up in that the areas that I saw that had low coherence tended to be like co-located with those zones of high deformation, but that was about as far as I went into trying to do that. So yeah, I'm coming at this from a more remote sensing aerospace background, so I am definitely interested in any applications that you all see, or like if you see anything interesting in the data, like that, I think those are all areas where I would be really interested in looking into it, but I don't have as much background, so I appreciate any feedback you can give.
All right, I have questions for two people, so I'll start with Sophie since you have the mic. So I actually have two questions for you. What is the range of length scales that you are basically able to measure, like horizontal length scales in terms of roughness? And have you thought about constraining roughness spectra rather than just like the integrated roughness amplitude that you're getting?
Yeah, those are good questions. Roughness is a complex parameter because it is so scale dependent. So the GPS wavelength, the L1 wavelength is 19 centimeters. So that gives you kind of an order of magnitude of what I'm seeing. I haven't thought about doing anything with spectra, but I do know that's a common way that people try to quantify roughness. And also the way I got roughness when I was trying to compare it with my data was at very first order, I'll say. I was trying to use the RIMA elevation model as a way to compute roughness as the standard deviation of surface heights. But obviously that's a 2-meter resolution, and my measurements have a 19 centimeter wavelength, so it's not quite a match. So I have been interested in trying to use something like ISAT2 data, because you could get like a long track LiDAR roughness profiles, and I think with something like that, it would probably be more feasible to look at an entire roughness spectrum rather than just one like standard deviation of surface elevation value.
Great. And then my other question is for Eric. And it has to do with what are the prospects for using your method to extrapolate instead of gap fill? Could you push the altimetry measurements further back in time? Would you want to?
That's a good question. Yes, if I have, so if I have a data set that I can use to control the extrapolation, I can push. For example, we know that oftentimes the penetration within the radar measurement is caused by the ice dynamics. So like the different structure that we have between the fresh snow layer and the firn layer. So if we remove that signal from the raw measurements, we can have a signal that we can attribute to the ice dynamics. And we can use that signal with, for example, the velocity to extrapolate out of the time series that we have. So it can be done. And maybe we can also do that with additional data set, but we just have to make sure that we are not using any type of data set just because they exist, but they need to have some sort of relation between each other so that we can use them to extrapolate.
Thanks.
All right, I have a question I'd like to throw to all of our panelists to comment on. So we've heard a lot of interesting advances in a variety of methods here that are sensitive to very different parts of the glacier, all the way to the bed, more to the firn layer, maybe at the very surface itself. I'd be curious the perspective from all of you on the prospects for joint inversion or for using various methods across sort of all of the remote sensing spectrum to get maybe better fidelity on some of these processes or better constrain sort of the gaps or open variables in your own inversions that you need for the data that you're working on yourself. So from each of you, it would be great to hear something.
I don't have immediate thoughts on joint inversion. I don't know that I have any really strong thoughts on doing joint inversions, but I can kind of use this as an opportunity to talk about something that I try to pitch briefly in my talk, but I think that doing something like this requires lower level data products. So if you want to think about incorporating lots of different data, you can't take the data products that are at the very top, which are often made public. And this is great. Like, we've made a lot of progress in open sourcing data products, and we can do a lot more collaborative work and new work based on how data are made available. But if you want to think about going across many different data sets, the pieces that you need from each might not be the piece that's at the very top. So having the lower level data products available might enable some of that type of work.
Yeah, I think that's a great point too, just thinking from the perspective of like if I were trying to compare to something like ISAT2 data, I think the lower level products are really helpful. I think with GNSSR, it almost has to be used in combination with other methods, at least at the stage it's currently at. It's very early and not well validated, and it also has issues in that it's extremely noisy, and I've been having to average a lot of data. But I think eventually where I'm headed is to do altimetry with GNSSR, which is possible and has been demonstrated. But I think for that, it's relative altimetry, or it tends to be relative altimetry relative to a different data set. So it almost by definition would have to be combined with a data set like ISAT2 or any sort of accurate altimetry measurement could be used to kind of ground it, and then ideally, what I would see for GNSSR is that it could be used to improve coverage and temporal resolution, but it would have to be anchored to a more less noisy, more accurate, like ground truth data set. So yeah, I think it's really exciting to hear about everything else that's out there, and I think it's exciting to have all these methods used together.
Oh, no, Eric, go ahead.
So I was just going to add that usually the idea of implementing joint inversion is always like welcome, but again, we need to make sure that the information that we are bringing together match in the way that one will help the other. So if we have, for example, two data sets and they are not really correlated, but we try to use them within the joint inversion, the solution that we will have can be fancy, but still unstable or maybe unrealistic. So I was just I'm going to say that at least we need to make sure every time that we want to do that kind of work, we need to make sure that the inputs have like a connection, something that correlates them to each other so that we can use them within a joint inversion.
right, we question. Otherwise, you're going to be forced to hear me indulge my radar questions for Ben. All right, I'm going to ask it anyway, and you guys can think you have one last chance to come up with something. Okay, so we're going deep dive on this one. I'm really curious about your Doppler spectra on this squint processing, because there were some very deep layers that look like they almost have a bimodal distribution in the Doppler spectrum, which I was surprised about. It seems maybe not aliasing based on the range you're looking over. What's your speculation? Like, what is going on in those deep, super sloped layers, like in the middle of that radargram?
Yeah, I'm interested in kind of digging into this with you and Dusty. In the pulse compressed image, you can kind of see it looks like layers at different slopes. I don't know exactly. I don't have a good answer for you, but I'm interested in chatting more about it.
Cool. Anyone else have a question before we go to break so I can make him speculate more?
Well, I'm just going to comment because that is a really important conversation, because as we're pushing the limits of some of these instrumentation techniques, like pulling out what's an artifact of just trying something new versus what is like pulling out a new layer from basal ice, that's a huge deal if it's real. And figuring out a pathway for us as a community to like buy into some of this, like what do we need to, how do we convince ourselves? You know, the reviewers are going to be in the room, so it's a question I struggle with a lot.
How do we convince ourselves that it's real?
Yeah, and it relates to Alex's question, right? Can we extrapolate? And then the answer is, how much do we believe that? You know, this is the through thread for all of these new method developments.
Yeah, I guess testing across different instruments would be one path. So I'm just going to keep harping on making data public. That if one group is really good about publicizing their data, and then you can do this type of analysis, it's interesting to compare across instruments and see if you, especially if they're in kind of a similar region. So that would be my first stab at trying to pick apart whether some of these signals are real or if they're instrument dependent.
All right, let's take a last question from Roger.
This one's for Eric. Really nice talk. Kind of piggybacking off of Mickey's question and a little bit, one of the exciting features of, you could call it kriging, Gaussian process regression, kind of that genre of statistical modeling is uncertainty quantification. And another kind of limitation typically is the stationarity of kernels. So the assumption that the amount of information that that propagates from one cell to another is similar across a spatial domain, for instance. And in Antarctica, that seems to be a challenging notion, given for things like roughness. So I wondered if you had thoughts about non-stationarity of spatial information passing and then also uncertainty quantification.
I think what I would say is non-stationarity is a challenging aspect of processing random functions, and there's a lot of idea out there proposing how to handle that. The one that I was showing today is just one, like trying to, so if you have a non-stationary random function, you try to imagine a specific order where you don't have that non-stationarity anymore. And so that order defines a new random function, which is just a derived of the initial one. And then you can use your stationary model on that new random function. Usually, I like that one because then I have less work into understanding how to process non-stationarity, because I already have the models for stationary functions, so I can use that one on the derived random function.
All right, let's thank our speakers one more time, and then we'll go to break.